Physics time, we're going to talk about work and energy. So write that down. Work and energy. I have a video just like this from physical science, but it's going to be slightly less in depth. Work, you know what work is, but work is different in science than it is in Taco Bell, right? Work in science specifically means to apply a force to an object and make that object move over a certain distance, right? So we have that work depends on force and distance. For you all, as opposed to physical science, it's important that you know we only, write this down somewhere, we only count the component of force that matches the distance. And we're going to talk about that in a second. But for now, what is W in this equation? Probably, you can guess. Work measured in joules.
So that's a force that matches.
Yep, that matches the distance. I should put matches the direction of the distance. Anyway, W is work, which is measured in joules. F is force, measured in newtons. And D is distance, measured in, as always,
Miles per hour.
meters.
Okay.
Just meters. It's a distance, right? Meters.
Wait, can you? I don't want to write.
What units, go back in your notes, what units is a Newton equal to? A Newton is equal to, what's that?
Isn't it equal? Oh, never mind.
In base units. You remember? You have it somewhere, so turn back real quick. We're on the clock here.
Isn't it a joule?
No, it's not equal to a joule. A joule is equal to a Newton times a meter, but a Newton is equal to a kilogram times a meter per second squared. Remember that? Well, you don't, but I'm telling you, a Newton is equal to a kilogram times a meter per second squared, right? Because force is measured as force equals ma, so force equals mass, which is in kilograms, times the acceleration, which is meters per second squared. So then if we multiply this, a joule equals
Wait, so does that M mean meters or mass?
This means meters. And then...
And the N equation?
What? Yeah.
N equals.
Yeah, this is a unit. These are units. And then a joule is equal to a Newton times a meter, right? Because we have force times distance, Newton times meter, which is equal to a kilogram times what's different about it now. If we have a Newton times a meter, now instead of being kilogram meter per second squared, it's kilogram times, no, meters squared per second squared, right? Because meter times this whole thing would be meters squared per second squared. A joule is a Newton times a meter, which is equal to a kilogram times a meter squared per second squared. And this is going to become very important when we get to our specific equations for different types of energy. Different types of energy. What are some different types of energy? Let's just list them off. Tell me some types of energy.
Potential.
Yep. Potential,
Kinetic.
energy, and kinetic energy. Those are the two main categories. These are what we call the mechanical energies. In fact, if we add these things together for any closed system, we call that, it's constant, and it's called mechanical energy. What's another kind of energy? Thermal, which is the kinetic energy of the particles. I'm trying to tell you, all kinds of energy are one or the other of these. There are some exceptions, like light energy really is neither one. But what other kinds of energy are there? Light? Chemical potential energy? What else? Can't think of any other kinds of energy? Thermal, light, chemical potential. What do we call the kind of potential energy that something has because it's high up? Do you remember? Did you read your books? That's called gravitational potential energy. And then we have such a thing as elastic potential energy. Well, what might have elastic potential energy? A rubber band would have elastic potential energy. There's also sound energy. There's all kinds of different energies. But these are the two that we're going to talk about today. When all of this is about work, and work, as you can see, work is measured in joules and energy is measured in joules. So work we can think of as the energy that it takes to move something. Both of them, work and energy, are measured in joules. When we're calculating work, it's important that we know that the force only counts in the same direction as the distance. So like if I should put this in picture. If I lift my book up, right? I've applied a force, right? I've applied a force and it moved a distance. Have I done work to it? Yeah, because I applied a force and it moved a distance. If I close the book and I'm just holding it here, am I doing work to it?
No. Yes, because you're still putting force through it.
I'm still putting a force on it, but is it moving? No. So what's the distance it traveled?
0.
0. So what's the work done?
0.
0. So if it's not moving, I'm not doing work. Now what if I am holding this up? What direction am I applying a force? Up. And I'm walking forward. Am I doing work to it?
Yeah. No.
No, because the force is up and the distance is forward. So they're in opposite directions, so that doesn't work. So where it becomes very important that we know how to do this, so only count the component of force that matches the distance. So what if Hadley, right, is mowing the lawn. This is how she mows the lawn. She just pushes it with this arm. She's mowing the lawn. She's applying a force, right? But she's applying a force down, we'll say at an angle of, it's below the horizon. So we'll say this is an angle of 290 degrees, okay? She's applying a force at 290 degrees. And the lawnmower is moving this way. Can we count her entire force? Maybe she's applying a force of 14 newtons. It's a very light lawnmower. Can we count the whole 14 newtons in this force equation?
Yeah.
No, obviously not, because we can only count the same direction that the distance is. So only which component of this are we going to count as the force? Which component? What do we call it?
The mower.
Yeah, what do we call the component of the force that is in the same direction as the mower?
Variable.
Here's our axis.
The
The x-axis. So we're going to do cosine, so 14 newtons times the cosine of 290 degrees is going to give us the x component of her force, and then that we would plug into this. This is extremely important. I see that you're not taking notes, but it is very important because this is all over your test. You have to be able to break down forces at an angle to find which one do we actually use. We can't use the whole 14 newtons. What is the answer to this? Does anyone have their calculator? We'll say that she travels, what's a good distance you would travel mowing the lawn? D equals, well, let's say my lawn's about 50 meters long one way, and I go back and forth maybe 20 times. We'll say 1,000 meters. She travels a kilometer mowing the lawn. That's not unusual. So distance is 1,000 meters. The force we don't know, because this is going to be f of x is all we can use. F sub x, sorry. What's the answer?
4.7.
4.7 newtons. So then we just do W equals FD. W equals 4.7 newtons times 1,000 meters equals W equals 4,700 what? Joules. Joules.
Okay.
Only the force acting in the same direction as the distance counts. Only the force acting in the same direction of the distance counts. So, just as an exercise, if I'm once again holding my book up, what's the direction of the force I'm applying? Up. I'm going to draw me now. I'm going to draw me. Okay, and I'm applying a force probably, let's say about 230, no, that's not right. Sure, we'll just say it's a light book. 230 newtons up, I'm applying it. So what's the angle of my force? Yeah, up is not an angle, but 90 at 90 degrees. Okay, and I'm traveling forward. And let's say I walk 2 meters. Okay, D equals 2 meters. F equals 230 newtons at 90. Well, let's just do it as we would. So what we have to type in, 230 newtons times the cosine of what?
Cosine
Of 90 degrees. Type that in your calculator real quick to find the work I'm doing to the book. Tell me, Taylor.
I got 0.
0. So
Yeah.
F of F sub x equals 0. So W equals 0 times 2 meters. Well, that's easy. How much work did I do? 0. I did no work to the book. So get out of your head the word work to mean like I'm working at Taco Bell today, right? Because that is not this. Did I do work in that sense? Well, I'm at my job, so yeah. But did I do scientific work? No. Separate these things completely in your mind. Scientific work.
Zero?
Yep. Yep.
Is that what came out of the calculator?
Yes, and it's also the truth.
Okay.
Get this work separate from the work you do at... Do you guys have jobs?
Yeah, that's summer.
Oh, at lifeguard. This is not the same as working at the lifeguard, right? Get this completely separate from your brain. Are you not a lifeguard anymore? You were once upon a time. Information booth. Okay, yeah, get that. These things are completely different. When your test says calculate the work, this is important, right? It doesn't matter if it says Bertrand is at the Dollar General stocking shelves and he does. Don't worry about he's actually at his job. Worry about how we do the math. Do you have questions about this? Do you see why the trigonometry is important?
Yeah.
Do you see why the trigonometry is important?
So are we always going to use cosine?
Well, no, because the distance is not always going to be the x direction. You only use, so for instance, if the distance were, if it were actually moving up, but the force were applied in a different direction, then we'd have to use something different. Because the distance can also be at a different direction too. So it's not always going to be cosine. No. The answer is no, it will not always be cosine, but you have to do your vector addition of this to figure out what it is going to be. Other than Jada's good question, right? It's not always going to be cosine, so get that out of your head too. Other than that, are there any other questions?
Can you go over vector addition?
Can you do
What
one
we
where
did?
don't
There's a
have to
video
use-
about that you can watch about vector
Can you
addition.
do
What?
one example where we're not using cosine?
Okay, sure. Let me make some more room for myself. So we'll say, let's say that, what's something that people throw?
Baseball.
No, that's too boring. A cat. Morgan throws Roosevelt
That's a whack.
because she's mad. She throws Roosevelt.
That's a big cat.
You drew her very skinny.
Oh. Okay. Morgan throws Roosevelt, and Roosevelt is falling. That's the path Roosevelt will take, right? And when Roosevelt, I'm not going to draw that whole thing again. When Roosevelt is right here, we'll say that she is traveling at an angle of, what is that? Let's say 200 and theta equals 320 degrees, okay? And she's at that exact angle, she's going to travel a distance of 0.3 meters. Okay? Good with that so far, right? That makes sense at this point. So she's going to travel a total of 30 centimeters at that exact point in her flight over the next however long, okay? And we'll say, what force is causing her to do this?
Me.
No? You're not. You're clear back here. What force is causing her to fall?
Gravity.
And what direction does gravity always act?
Down.
Yeah. Gravity is always acting down. So
Is that
F
it?
sub g
What is that?
is down.
X or 0.3
3 meters. D equals 0.3 meters. F sub g,
No, not that. What?
What?
320.
320. F sub g equals, what about is Roosevelt's weight, would you say?
Like 20 pounds.
20 pounds. So that would be about 45 kilograms. And so that's, and I don't mean 45 kilograms. 20 pounds. Let's say she's 22 pounds. She's 22 pounds, isn't she, Morgan?
Yeah.
That's 10 kilograms. That's a lot easier. 10 kilograms has a weight of about 1,000 or 100 newtons. So we're going to say her F sub g is 100 newtons. And by the way, since this is straight down, what angle is this always at? What angle is that? Well, up was 90. What's down?
180.
180 is that way. Nope.
270.
270 degrees. We can only use the forces acting at that distance. So we're still going to use that equation, W equals FD, but now we need to figure out how much of gravity we can plug into here. So basically, we actually need to find out what distance is she going to travel, but only down. It's kind of the reverse. Before we were thinking, what force am I applying in the same direction as distance? But now we're going to think, what distance is she going to travel only down? So what part of this, what component of this do we need to find? The y component. So in this case, we need to find the y. So it's going to be f sub y, d sub y, the distance she's traveling only down, equals 0.3 meters, right? You see, this time it's not even in a force, it's meters, but meters have a direction too. Times what? Sine of 320 degrees. Boop. D sub y equals, someone fast on your calculator.
Why did we do that?
Because we can only, the force is always going to be acting down. So we can only use the distance that's acting down
What did
to.
that say?
320. They have to match. It's only what's matching about it that counts for the work.
-0.19.
Negative 0.19
Yeah.
meters. Okay? So her work, we're just going to get rid of the negative. That's just a direction at this point, but 0.19. So W equals, what's the force? 100 newtons. What's the distance she travels in only that direction? 0.19 meters. So her work, the work that was done by gravity on her is 19 joules. Does that make sense?
Yes. So basically we're just using sin and cos.
Right, we can only use sine and cosine for this probably.
It just depends on the angle.
Right,
of it.
right. And it could happen that some other force was applying here that was at an angle also. So they might both be at an angle, and then we have to find what part of them matches. Because we can only, once again, for the fourth time, we can only use the force and the distance that match up together to calculate work. They have to be the ones in the exact same direction.
Which equation did you use when you did d sub y?
0.3 meters times sine of 320.
Yeah, what equation did you use and why did you choose sine?
This is not an equation, this is just how trigonometry works. Because we can only use the y component because that's the direction gravity is acting.
So why did you use sine?
Because sine finds the y component for a triangle. For our triangles.
Cosine finds x,
Yes, cosine finds x.
and then tangent is
Well, not always, it depends. Because
The
we
degree.
have, what we're given is the hypotenuse. So since we're finding the hypotenuse, since sine is opposite over opposite over hypotenuse, and we're multiplying by the hypotenuse, sine will find us not necessarily y, but it'll find us the opposite side of our triangle. And if our angle is here, the opposite side of our triangle is this, which is what we want to find. D sub y. Okay? Questions more about work? I appreciate both of your questions. You have more of them? Okay. Okay, so we're going to move on. So work, like we said, work and energy have the same unit because work we can think of as energy that moves an object, right? Is there other kinds of energy? Does every kind of energy, I'm trying to ask you, does every kind of energy cause work to be done?
Yeah.
Try again. No, yeah,
Yeah,
you're right.
yeah.
Yeah, because think about thermal energy, right? We even saw in the video yesterday that thermal energy we think of kind of as like the wasteland of energy. Thermal energy generally cannot do useful work. You might even write that down. Thermal energy cannot do useful work. That's not always true, like a steam engine. But thermal energy does not do useful work. Where does thermal energy come from?
Heat.
Yeah, thermal energy is, in one way, thermal energy is heat, is the heat an object has, is caused by atoms moving, and one way that thermal energy can be formed is,
Thermal energy is not useful.
not always, but thermal energy doesn't do useful work. And that's not always true, but in general, that's where that's like the graveyard of energy. But as mechanical energy, which is either potential or kinetic, turning into thermal energy, what do we call it when energy changes types?
Energy transfer. Mechanical.
Yeah, this is an energy transformation. What do we call it when energy changes from one object to another?
Energy transfer.
And transfer. So if I throw that eraser, which I did, and almost knocked over my coffee and then almost broke my computer again, if I throw that eraser, I've transferred mechanical energy from my hand to mechanical energy in the eraser, right? So that's just a transfer. So it's still mechanical energy, except it's in the hand, becoming same mechanical energy, but it's now in the eraser. This is just a transfer. An energy transfer. Anyway, so we have a specific word for this whole thing. When mechanical energy becomes thermal energy, we call that friction. And we learned about friction in terms of force before, but now we're learning about friction in terms of energy. Speaking of mechanical energy, we said before, mechanical energy is made of two things mostly.
Potential and kinetic.
Let's calculate those. Potential energy depends on what? Potential energy is represented with U. What does it depend on? How can something have more potential energy?
Height.
It depends on height. The higher up it is, the more potential energy it has. What else?
Mass.
And the third thing?
Gravitation.
Gravitation. So U, specifically this is gravitational potential energy, equals mgh, where U is as we said, potential energy, measured in
Joules.
M is,
Mass.
yeah, I'm always going to be waiting for you to fill these in. Measured in, what's the base unit for mass?
For kilograms.
Kilograms. Grams are too small, so we use kilograms. Lowercase g is,
Gravity.
yeah, we call it acceleration due to gravity. And we measure that in, nope, that's the force of gravity. Acceleration due to gravity is
Meters per second squared.
meters per second squared. And h is
Height.
height. Measured in the SI,
Meters.
meters. Let's check out our units. Kilogram times meter per second squared times another meter is kilogram meters squared per second squared. Oh, that's familiar. What is that? What's a shorter way to write kilogram times meter squared per second squared?
What?
What's a shorter way to write kilogram times meter squared per second squared?
Kilograms.
Joule.
times-
It's a joule.
Oh yeah.
It's a joule. That's why potential energy is measured in joules. It's because these things, when we multiply the base unit for mass, kilograms, times the base unit for acceleration, meters per second squared, times the base unit for height, we get meters squared times kilogram per second squared, which is the same as a joule. As something falls, I usually have an object that can fall. This one. As something falls, so if I started out up here, right, it has a certain height, I don't know what it is, probably about 2 meters, right? It has a certain mass, and it has the acceleration of gravity on Earth is 9.8 meters per second squared, right? As it falls, what's happening?
It's accelerating.
It's accelerating. Good. That's exactly what I wanted you to say, which means it's what is increasing.
Momentum.
Yes, technically, but also I'm looking for something more specific. Its speed or velocity is increasing. You're right, Morgan, but yeah, the speed or velocity is increasing. What is decreasing?
It's
The
height.
distance.
It's height. Yeah, the distance from planet Earth. Its height is decreasing. So its potential energy, because of its height, is going down. What's going up? Kinetic energy. Right, so if something falls, kinetic energy is increasing. Kinetic energy is K. What is kinetic energy dependent on? We already said. You said it already, Jada. Yeah, so it's mass. If it were larger, it'd have a higher kinetic energy. What else, though?
What?
What else does kinetic energy depend on? Velocity. And remember, it doesn't just depend on these things, because this is, mv is momentum. But this, we have 1/2
1/2 and
mv squared, where K is kinetic energy measured in, good? 1/2, you know what 1/2 is. M is, once again, mass measured in kilograms, and V is velocity measured in, what do we measure velocity in?
meters per second.
Meters per second. What happens if we square the quantity meters divided by seconds?
Then it becomes acceleration.
No? If you had a math problem that looked like this, what would the answer be if we simplify? Or if we distribute that square?
1/2 meters. Well,
We're not deriving it. We're not deriving it. We're just, there we go. It just distributes. So that times kilogram, what does that give us? Kilogram times meters squared per second squared is joule again. It's the exact same, it ends up with the exact same units, it's just another way to get there.
K is energy. Is that a joule?
Yep. What quantity in this equation does the kinetic energy depend on the most? Like, which one will affect it the most if it changes?
Velocity.
The velocity, right? If we double the velocity, what's going to happen to the kinetic energy? Nope. Yeah, go by 4 times. If we triple the velocity, what will happen to the kinetic energy?
6 times. 4 times. 5. What did you say?
If we triple the velocity, if we have instead of
3
v,
times.
nope, triple the velocity, which is 3 times, what will happen to the kinetic energy? Well, if we triple it and square it, that's, what's 3 squared? 9 times. What if we quadruple the velocity? 16 times the kinetic energy. It goes up really, really fast. The faster a thing moves, its kinetic energy increases very rapidly, more rapidly than linear, right? It increases as the square of the velocity. This happens with your braking. That's why if you double your speed, if you're driving 30 miles an hour down the highway, it's going to take you a certain distance to stop if you hit the brakes, right? Some distance. If you slam on the brakes as hard as you can, it'll take you some distance to stop. If you double your speed to 60 miles per hour, how much farther will it take you to stop? Because of this. If we double the velocity, it's going to take, the energy is depends on how much, or the energy determines how long it takes you to stop. So it's going to take you 4 times as long to stop. If you triple your speed to 120, nope. If you quadruple your speed to 120, how many times farther will it take you to stop? 16 times farther, right? So it's not a linear relationship. That's why there are speed limits. Do you think it's because the man wants to keep you down? The reason is that if you're driving at night, there's a distance your high beams will spread out onto the highway, right? They're only going to show you something so far away. They're not going to show you something 23 miles away, right? Like you can see at daytime. So the way that speed limits are determined is if a car with a normal length of high beam sees a deer in its headlights right away and hits the brake, it'll take it this long to stop, right? And if you're going 120, if you see a deer, there's physically, not only if you stopped immediately, like if you hit your brakes as hard as you can in the very best car in the world, there's physically no way you could stop before the deer was at you. Do you see what I mean?
Yeah,
because of this.
So I saw this video and it was about this paramedic who was at the scene of a crime and they were doing like investigations to see like when the guy started to stop. And it was like if he was going 60 when he decided to stop, she would have been able to like stand up and walk away.
Exactly. Yep. They do this all the time. I don't know if you heard it in the microphone, but they do this all the time with insurance adjustments. This is how they determine who's at fault in a car crash. They measure the length of the skid marks, and then they use this equation or something like this equation. They probably have a calculator that does it, but they use this equation to determine, based on this length of skid marks, they were going this fast, and therefore they were speeding, and therefore they broke the law, and therefore they're 100% at fault, right? And if they weren't speeding, then maybe they split it, and both parties have to pay for it. But this comes up a lot in insurance adjustment and in crime scenes. Yeah, very good. I'm glad you brought that up. Before we go, I'm going to talk about 2 more things. Conservation of energy, which you should know about already, but the conservation of energy. Sometimes called the what of conservation of energy?
Law.
The law of conservation of energy. Laws in physics mean, if you remember from chapter 1, mean that this is always true. It's not an explanation why it's true, it just always happens. The law of conservation of energy is one of the 3 fundamental laws of the universe. And this one tells us that any amount of energy, anytime energy changes, it's the same amount before and after. So then how come, if I drop my sugar skull, it doesn't just keep bouncing forever? Do you remember we talked about this yesterday?
Air resistance.
And?
Gravity.
Well, so it's potential energy is becoming... So if this were true, it seems like, If this were true, it seems like potential energy, kinetic energy as it goes down, back to potential energy forever, right? But because there is friction, some of that is lost to thermal energy. And because there is sound, some of it is lost to sound energy. And because it squishes as it lands, some of it is lost to the shape, the movement of the atoms that make its shape change. Do you see what I mean? So all of that comes into play, meaning that this is still true. It's just that instead of it being always always kinetic and always potential, it's now kinetic and potential and thermal and sound and deformation, right? So this thing is still true. It's just that we have to consider more types of energy. And then lastly, we talk about machines real quick. Write down machines. You have this, I think it was a vocab word. But machines are something that make doing work easier. But they can't change the amount of energy done. Sorry, the amount of work done, which is the same as energy. Machines make doing work easier, but they can't change the amount of work done. So what are some ways that machines can make your work easier? They can, what 2 things can they change? They can't change this. This has to be the same in both cases. Work in must equal work out.
Well, I thought we were naming machines.
We can, but what is work made of? This is the same. Let's substitute this for something simpler. This is the same as what? F times D, right?
Yeah.
F times D.
A bike.
Yeah, so how can that...
Makes traveling easier.
So in order for it to make the distance that you did the work smaller, what must it do to the force?
Make it bigger.
It must get bigger. So if the force gets bigger, if the force gets smaller, then the distance must get
bigger.
Right, it's this principle, right? So if I want to apply less force, I have to apply it over a greater distance, like an inclined plane, right? If I want to, the classic example is here's my moving truck. This is how you drive a truck. And I've got to lift, it's a moving monster truck, and I've got to lift my piano into it, right?
Oh my gosh.
If I got to lift my piano into the
With
truck,
one hand.
I have to apply it over a certain distance, but I have to apply a larger force. Whereas if smart old Hadley comes along, oh wait, Talon hasn't been a part of the drawings yet. If smart old Talon comes along and uses an inclined plane, same piano, but now instead of applying that much force, she applies the force over a longer distance, but it's a smaller force, right? That's why inclined planes are good. That's why all machines
It's
work.
like if you're trying to drive up a straight hill and
Efficiency, efficiency equals work out divided by work in times 100%. Looking at this, can efficiency ever be greater than 100%? Which one of these must be smaller? The work out or the work in?
work in.
Nope, try again.
Work out.
The work out must be smaller. And so can this ever be greater than 100%?
No.
No. Can it ever in reality be at exactly 100%?
No.
Probably not, because this work out is always going to be a little bit less because of
Energy transformation.
specifically which energy transformation? Friction. Because of friction, it'll never be quite 100%. Nothing is 100% efficient. There's also an equation for power in here, but you're going to have to do that on your own because we're running out of time in our video. But basically it's this. Power equals energy divided by time, and it's measured in watts. We don't have time to go over the whole thing, but power is in watts. You know what energy is measured in. You know what time is measured in. So you can go from there. But that's all we have time for unless you have a question that we can answer fairly quickly. Yeah? Yeah, good?
Yep. Good.
Good.